What I want to do in this video is show you the graphs of these three equations to see how they are different. And what we're going to do is focus on the horizontal as well as vertical asymptotes and maybe a whole to be able to really kind of understand the impact of having an expression in your denominator as well as having one in the numerator and the denominator. So let's start with the easy one, the one that we probably are the most confident on saying, oh yeah, I can go ahead and graph that. I remember that. We have an equation y equals x plus 2, and we remember that this is RD in slope-intercept form. So remember 2 is going to represent our y-intercept, so we go to 2, right? And then we can say our slope is 1 over 1, so we can go up 1 over 1, and then go ahead and connect our graph, or we can go down 1 to the left 1, and still, it doesn't really matter, but that is what our graph looks like. And when we're talking about discontinuities, right, those are going to be breaks in the graph. So when we don't have any discontinuities, we could say the domain is going to be all real numbers, okay? So this domain is going to be all real numbers, the range is also all real numbers, and yada, yada, yada. All right, so now let's go and take a look at this next example. Now, this next example, we need to have a better understanding of the asymptotes. You can still apply the same rules to asymptotes in here, but I'm going to talk about, I'll go back to that in just a second. So let's go back over to this one. Now, we can't simplify anything here, right? So what we have to do is understand our rules for our asymptotes. Now, when there's no expression in the numerator, we can say that that still has a x to the 0, right? Because what is x to the 0? X to the 0 is just going to be a 1. So by using our horizontal asymptote test, we can say whenever the degree in your numerator is less than the degree in the denominator, right? Because this is technically x to the first power, we have a horizontal asymptote at y is equal to 0. All right, now let's go and take a look at our vertical asymptotes. Remember, vertical asymptotes are going to occur when our denominator is equal to 0 as long as it did not get removed. That's what we call our removable discontinuity, which creates a whole. Well, we can't remove anything, right? Because there's no way to simplify this. So my vertical asymptotes are going to be the values that make my denominator equal to 0. We could plug it equal to 0, but in reality, guys, we know that the value is just going to be a negative 2. Right? Because when you plug negative 2 into this equation, negative 2 plus 2 is equal to 0. So there we go. All right, so now let's go ahead and graph this. So in this case, whenever we're graphing with asymptotes, you might not know what this graph looks like. You might already. The main thing that I want to come across with you is let's go ahead and plot our asymptotes. So we have a horizontal asymptote at y equals 0, and we have a vertical asymptote at x equals negative 2. Okay, now, a lot of times we want to go ahead and pick some points on this graph to be able to identify where the points are going to plot. So what I'm going to do is I'm just going to go ahead and pick, well, why don't we pick x equals 0? Because that would give us our y-intercept. When we plug 0 in for x, we're going to get a 1/2. So let's just say, there's a 1/2. Now here's the interesting thing. Horizontal asymptotes can be crossed based on the function. In this example, they're not. But the main thing that I want you to understand when you're looking at graphing is your graph always has to approach your vertical asymptote as well as your horizontal asymptote. And guess what? That's going to be the same thing on over here. You can't draw anything else over here, right? Because then it wouldn't be a function. And then if we pick another value, let's just say negative 3, well, that's going to turn negative 3 plus 2 is going to be 1 over a negative 1. So that'd be like down there. So like negative 3, we're going to be at like negative 1. So what's happening here is now, again, I have to approach my two asymptotes. All right. Now in this case, my domain is not all real numbers. My domain is going to be all real numbers except for where my vertical asymptote is. So let me actually write in my domain. Domain here, all real numbers. Domain over here is going to be all real numbers except for a negative 2. But we knew the graph based on our horizontal and vertical asymptotes. That's what helped us. And then you can just choose some plotting the points and just make sure your graph is always going to be approaching those asymptotes. Now let's go and look over this equation. Now what I want you to recognize this is we actually have the exact same expression or the exact same expression, all right? So let's go and take a look at the horizontal asymptote is not going to matter here because this is going to divide to 1. Now can we graph that using the slope-intercept form? Yeah, like that's technically a slope of 0, but it has a y-intercept of 1. So I can go and graph that. However, remember, we have something that was still in the denominator. So we always got to look for our discontinuities. What is the value that makes my denominator equal to 0? We say it was negative 2. Well, you can't have negative 2 in this problem. Like, of course you can have negative 2 for this equation. But again, this graph is just a simplified version of this graph. Negative 2 is an undefined value. Well, it can't be an asymptote, right? Because asymptotes are non-removable discontinuities, ones that cannot be simplified. This got removed. So therefore, this creates a whole. So this graph is going to look like this with a whole at negative 2. However, the domain is going to be the exact same as this domain. And there you go, ladies and gentlemen. That is how the denominator is going to impact your asymptotes for vertical asymptote as well as when you have a whole. I hope this video was helpful for you. If you want more videos on rational expressions, check out the playlist I have for you down below. Cheers.